Okay. Well, good evening, everyone. And so this astro-café is looking at two topics. The first one here is about a tool for helping you plan your Noctilucent cloud observations. And I created a website mostly to help myself. Of course, when you do a website, it then is available for other people to benefit from. And so the website is very simple. It's only got 3 utilities: a timetable for viewing, an apparent cloud motion schematics, and a graph that shows the overall annual progression. And I'll be explaining a little bit about each of these as we go through. Because it has to advance through clicking. Okay, I will try and not cover things that I touched on at the main meeting about Noctilucent clouds, but I will recapitulate here that they are from the Latin meaning shining at night, and you will always find them in the twilight arch. Sometimes they're very subtle, and sometimes they're very, very prominent. And we only get about 3 of these super nice displays per summer season. And you'll always find them in the twilight arch because they need to be lit up by the sun, which is beyond our horizon here in Edmonton, or in the mid-northern latitudes where the sun dips only a little bit below the northern horizon and still is illuminating the upper atmosphere. So typically when people want to see Noctilucent clouds, it's a display like this, bright enough so that in a single exposure you can take a picture of both the clouds and a nice cityscape or a nice foreground, or things like this with oodles of waves and curls in them. So there's a few challenges with this, and I'll be going over them shortly. The key thing to note here is that Noctilucent clouds are very thin and transparent. And so here, as I'm circling this patch of NLC, is what was really in the sky at the time. But if to show how the contrast is so delicate, is that if I copy this and paste it into a lighter area, allowing the lightest things to show through, as the sky gets brighter, they just overwhelms the Noctilucent clouds. But if the clouds are in an area farther from the twilight, they can be quite bright. And that relative brightness is mostly just about the contrast that it has against the background sky. And that contrast depends completely on timing and geometry. And so the geometry is all about how far the sun is below the horizon. So that's why the number here is negative. So here the sun is 10 degrees below the horizon. And the part that is lit up, as you see the clouds coming in here, is up at 80 kilometers altitude, whereas the super deep blue, which is pretty dark, is 120 kilometers up. So the high atmosphere is being lit up by the sun, but lower down at 80 kilometers, there is Noctilucent clouds right in this dark blue spot. It's just that the sun is below the horizon, even for them being up at that height of 80 kilometers. As the sun gets higher in the sky by the sun, when the sun is only just a little bit below the horizon, and the contrast is enough that the clouds here can show up against the deep blue. The area down here closer to the horizon does have Noctilucent clouds in it, but the sky is getting so bright that it's just blowing out the exposure. here. There we go. So for the geometry, this is looking north to the right and west into the page. And so with an observer here looking north, the sun is just below the horizon. And this is the shadow of the earth, this orange line, and everything below that orange line is in darkness. But the Noctilucent clouds 80 kilometers up are still in sunlight, everything in white here. And the range that we can see in the sky is all dependent on this solar angle. And I'll show you in a moment how that changes. So when the sun is minus 10 degrees, a lot of the atmosphere is in shadow, but we can see everything below this purple line down to the black line, which is at the horizon. All of that, any Noctilucent clouds in there, we would be able to see because they're in sunlight. But this angle here is only 15 degrees. So even if you do have Noctilucent clouds higher up, they're in darkness. And as the sun gets higher in the sky in the morning, the angle is much lower here. And all of a sudden, this whole area of the sky straight above the observer is now in sunlight. And so this angle going from the northern horizon looking south gets you to 165 degrees. So that's almost full sky by the time the sun is minus 6 degrees. And then when you get late at night and increasingly towards August, away from the summer solstice, when the sun is quite a bit below the horizon, the Earth's shadow is much higher in the sky. And even this zone at 80 kilometers up is only a very narrow zone that is lit up by the sun that we can see from our point. And that turns out to be a mere 5 degrees off the horizon. So even if the sky was completely covered in Noctilucent clouds through here, we would not be able to see it because the sun is too low. So that's the whole bit about geometry. And of course, at this point, you might be saying, oh, geez, that's an awful lot of stuff to remember. And that's why I made this page, because I don't like remembering all that stuff and having to try and figure it out each time. So that's what the website does. You just plop in, well, the default latitude and longitude is for Edmonton here, but you just click on this evening and this timetable comes out. It tells you when sunset is and what the solar altitude is. I've put in the key values here at when the sun is at -4. You could start seeing Noctilucent clouds on the far side of the sky where the sky is starting to get dark. But it turns out that the best contrast is somewhere when the sun is about -9. And then by midnight, that's when the sun is lowest. And we're talking here astronomical midnight when the sun is due north, and which turns out to be 1:35 for us here, 1:35 a.m. And then of course the sun starts rising yet again. And so the key thing in here is to pay attention to when these best contrast times are and when the earliest times are. And I'll give you another example shortly. So, for example, Mike Noble would say, he'd send an email saying, oh, there's a hint of NLC at 10:40 p.m. And you might go out and, oh, yeah, there's this little bit here. And you go, well, that doesn't look like much of a display. I'm going to bed. It's almost 11 o'clock. And so if you have a life, Noctilucent cloud hunting is almost a showstopper unless it's the weekend. Is just looking at something like this is you can't tell that 1 hour later you've got this awesome display going on because the sky has gotten dark enough that the NLC can now be brighter than the darker sky. But of course, it's too late. You're in bed and asleep, so you've missed it. And the challenge is that these times for the best time is hard to remember, and that's why we use the utility. So I'm going to try this new share, and it should say advanced video, and it's not on here. Good Lord. That's amazing. It was the last time. Well, that's a little disappointing. Huh. Okay. We're going to go, I guess, have to exit back, go stop share, go back to share screen, and I'm going to have to toggle over and do this the lower tech way. I apologize for this. That should have worked. It worked when we ran it in practice.
That's the problem with demos.
Okay, so this is what we call the morning jump, where as the sun gets higher in the sky, suddenly the higher parts of the sky get illuminated, and they get illuminated very quickly, and the NLC looks like it just jumps from very low in the sky to quite high in the sky. And there's the equivalent slump in the evening. So I'll just run that again. So at the start, there is Noctilucent clouds in this darker part of the sky. It's just not yet illuminated.
So how long is this time lapse, Alistair? This is like 15 minutes?
No, it's about an hour.
Okay.
So the key part, get back to here, is when I'm using the planner, and I'm going to bed because there's no Noctilucent clouds in the evening. And so I would then look at when is this jump in the morning, and this practical maximum altitude shows you the jump goes from 10 degrees high to just under 30 to 60, all in a range in a very short time span of 15 minutes is the jump. And so the key thing is how quickly can you get out of bed, as in once your alarm goes and you actually see that there's Noctilucent clouds there, how quickly can you say, get in the car, drive, set up your camera and start shooting? Because quite often it's, well, by the time, if it looks like it's a great display, well, you've already missed sort of the best 15 minutes of it. So the thing to look at is what the maximum altitude is. So for example, I would set my alarm somewhere, say for example, if it's going to take me 15 minutes to actually get out of bed and well, check the sky and then hurry, put on some clothes and drive to the nearby park. If I say that, well, that's going to be 15 minutes. So I want to be there at this point. So it's like, okay, I'll set my alarm 15 minutes before 3:10 a.m. And then when I check the sky, it's if the Noctilucent clouds are already at their maximum altitude, then there's a very good chance that they will continue to go up higher and higher as the morning progresses. As in, if they're there, they'll show up. Now, we don't always know that, but at least that gives me a fighting chance. But if I set my alarm for when they're for best contrast, I look out the window and go, holy shoot, look at that, it's amazing. It's like, well, by the time I get in gear and get moving, it's too late, or almost too late. So that's why I use this. And it's these times change so quickly once you're beyond the summer solstice of the 21st. For the upcoming week and the week after the solstice, these times don't change too much. But once you're past 10 days past the solstice, these times change pretty quickly, surprisingly quickly. So sometimes the Noctilucents are very subtle, and you can actually figure out whether you want to go to bed or not, or go back to bed when you wake up and you look out the window. And the other thing that's really key in here is the altitude of Capella, which is going to be the brightest star in the northern sky, because you can then compare Capella's altitude to the NLC. And so if the NLC, in this case, it says, well, the maximum they're going to be is 10 degrees or 11 degrees. And well, in this case, coincidence, so is the altitude of Capella. So if the NLC reach Capella, then you know that there's the NLC fills the sky at least to that height, maybe more, hopefully more. But if you see something like this and Capella is up here and you say, well, the NLC could be up there, but I can already see that it's not, then the chances of there being a better display later on are very, very low, because it would mean this area of sky ought to have the clouds there. So if the, as a summary, if the Noctilucents do not go as high as Capella, according to that timetable, then it's just like, go back to bed. So just a little bit of eye candy here and a reminder to use binoculars. Okay, the annual table hourglass, inverted or rotated hourglass, shows nighttime in black, daytime in yellow, and the twilight times that Noctilucents are seen from a solar depression of -4 to -16. So not quite the astronomical definition of -18. But once Noctilucents get to, or the sun gets to -16, we just cannot see Noctilucents anymore because they're all in shadow. And so the Noctilucents really start getting going in end of May and start of June, when we get into this middle zone here. But especially as we start getting towards August, we then can get a gap where we see a really nice display. The lights go out completely overnight, and then they restart in the morning. So it's an added benefit if you're a hardcore observer. You can get an hour and a half sleep while the sky is a bit too dark. And so the advantage of something like this is that it's very easy to compare places around the world. Up in Yellowknife, these stretch out completely, and you don't get much darkness at all. So that's just a convenient overall kind of planning tool. The other issue when dealing with Noctilucents, which will come into the third part of the planner tools that I developed, is when you have things like smoke. This is forest fire smoke and not Noctilucent clouds. And but they can have some of that similar structure. I believe, yeah, here's another one where you think, oh, here we are in twilight, there's these bands going across the sky, and you know, they might look a little strange, but of course, as it turns out, these are from smoke. And the big difference when you're following Noctilucent clouds is that as it gets darker and darker, the smoke will also get darker, whereas the noctilucents will brighten up as the contrast improves. But when you're in that sort of, the sun is -6 degrees down like it is roughly here, it can be hard to tell. So you're not quite sure whether this is a phenomenal noctilucent display or something a little more terrestrial. The other problem that happens is when you start getting around full moon and it's just normal clouds very high up, jet contrails and high cirrus can mimic noctilucent clouds. So you can look out and go, oh, we got something here. And then it's like, nope, it doesn't seem quite right. And what the 4-class cloud motion schematics help with is which way are those clouds moving? Take 5 minutes and see which way they're drifting, because noctilucents will pretty much always drift from east to west, and whereas most weather clouds down where we get the smoke and normal cirrus clouds, they'll be drifting from west to east. Now, of course, this changes night to night as the weather patterns change. And so again, it's something that, well, I don't want to spend all my time checking this stuff up. So this is what computers are really good at. Now, to use this thing, you'll see there's azimuths down at the bottom. So almost west to northwest to north to northeast to almost east. And so if you imagine whether it's a cloud or a plane moving from east to west, if you're facing east and it's moving from east to west, it just seems to get higher and higher and then will pass above you. And then if you turn around to face the west and watch it go past you, it looks like it's just heading right down to the horizon. Now, if you were, say, south of the city looking north, and the plane went straight over the center of the city, if you were facing north, it would look like it's just going straight right to left in front of you. And so with this sort of schematic, depending on where you look, the clouds will be moving in apparently different directions. So, I mean, it's kind of weird where you think, oh, this looks like it's rising, going sideways and falling, but those clouds are all moving in a constant speed in the same direction. It's just our perspective, like the way the railway tracks converge to infinity, that causes this type of perspective. The other thing that I've included in all this is that, for example, I know very low to the horizon that these clouds are actually 100 or 200 kilometers away. And so they're not moving with the same speed as the clouds straight above me. So that's all taken care of by the computer processing, and then the representation, like these arrows, this is how the clouds would trail on or shift if you're going to be doing a time lapse. And so, for example, if there were noctilucents looking north, as I'm going to show in the next movie, if the noctilucents were there, they would be going from right to left. Higher cloud are these dark blue arrows. They're going from left to right. And the very lowest cloud are these black arrows. They're hardly moving at all. So I'm going to set up that video. So as you can see, the cirrus here is moving left to right across as I'm facing north. And these white lines here, and I'll play the video again, are smoke, and they're sort of hardly shifting around at all. So it's one of those things, if they were NLCs, they would be shifting from right to left across here. So that is one of those things that helps me, especially during the moonlight phase of observing. to have a look at one of these schematics, which way are the clouds supposed to be going? Because every now and then you do get reversals of flow in the normal troposphere, where you get cirrus clouds which will mimic the same direction coming from the north-northeast or east-northeast and moving sort of leftward as noctilucents were. And if there's a full moon, then it would be potentially confusing. So it's a good way of double checking. I think okay, yeah, that was the smoke and cloud. Yeah, so here is the schematic for this evening. The very low cloud is moving very quickly from west to east. If you're looking straight west, they seem to be just coming up and up. If you're looking straight north, they will be appear to be moving sideways, left to right. And if you look towards the east, it looks like they'll be cutting down a lot. And notice how the higher light blue ones, which are the noctilucents, they would be moving the other way. So that really helps distinguish between the two. And of course, the farther away you are, the less they seem to move. And that's just, again, that trick of perspective that a high-flying plane is moving several hundred kilometers an hour, but because it's so far away, it just shifts very slowly against the sky. So very distant NLC would be going much more slowly, and similarly, the cloud in our atmosphere would be going more slow, appear to be going more slowly the farther away it is. And then just a reminder of how patchy things can be. Here is the latest Noctilucent cloud daisy. So it takes a whole day to create one of these things in these orbital passes. Excuse me. And so it's, unfortunately, it's always 2 to 3 days late. So you can't quite use this to predict things, but it's useful at least to illuminate the problem of, just because Quebec or Ontario is getting a good NLC display doesn't mean we will, because for example, this patch is very thick and broad, whereas another 30 degrees longitude over, and it's just very patchy, thin. And I will go to the next one, which has a close-up. And you can see how in some cases you just get these individual little blips. So for example, if you were living in Scotland, you might see something on the northeastern horizon or northwest horizon, but essentially nothing happening for you. Meanwhile, your buddies in Norway are raving about how fantastic the display is. Or if the timing is just right or wrong, well, maybe the previous night, all this patch of NLC was right over them. And then the next night, poof, gone. So it's very trying to watch for these NLCs. So I'm going to end with just a couple of sort of eye candy videos of time-lapsing. And this is again why you want to use binoculars, is you just get to see this incredible density of detail. Now, even in binoculars, you don't get to see it move like it does here, because this is about a 40-minute time frame. Go to the next one. This is actually a still panorama, but it again is showing the amount of detail that is visible. It'd be very similar to what you would see in binoculars, although I find, just like with anything else, reality has a much bigger punch to it than the an image does. And then one of the things that I've been playing with a lot is essentially moving, following the motion. So digitally, I'm shifting the camera to follow these long waves coming down. So I'm essentially panning on those waves, and everything else is moving relative to that. So I'll just start that again so you can sort of see them come in. So you can see much smaller detail moving through the waves as they come in. And those of you who've been on a marine coast and at a harbor might see these types of interacting waves. And a lot of those waves seem to be created by thunderstorms in the normal lower atmosphere, but the energy moves up through the, like ripples through a pond, moves up into the upper atmosphere and causes the waves up there. Now I'm going to show this again, but following the motion of the even smaller elements. And so, like if you just focus, say, on this patch here, and you can actually watch it, you can see the wave breaking as it smashes, and then it goes down the trough, up to the next crest, up and over, down again, up the next crest. You can actually spend sort of 30, 40 minutes watching and rewatching and these things. There's a lot of action going on just there. Hang on. So yeah, you can see these guys going up and over the crests. As the big waves come in, the smaller stuff just carries along with it. So there's different speeds of waves traveling in the upper atmosphere there. So I find that very mesmerizing. Okay, so that's the presentation about the different tools that I use for following Noctilucent clouds. So I will stop there and go back to the main page, and we'll just end up on a nice picture here. There we go. And I'll take any questions that you might have.
I got a question for you, Alistair.
Sure.
When Mike posts his NLC chase reports, he mentions, well, he refers to azimuth as RA. Is that like, what does he mean by RA when he indicate direction of, you know, or extent of the NLC? Like he'll say, oh, RA is from 310 to 030 or whatever. So I assume that he's talking about azimuth directions, isn't it?
Yes, that's right. It might have something slightly different from his surveying days. Maybe the RA has a different meaning, but for us, and when he uses it for us, we just take it as azimuth. So yeah, 360 and 0 is north. And
yeah, that's what I assume. But RA for us is right to center. So. Okay, well, I just assumed that, but he keeps on using RA, and you're like, what's RA anyway? So, and you know, so but he says altitude, so you know, like altitude's fine. We understand that. So
he's been doing the same thing for years.
Yeah,
for years, and it's just, I think it's just a little glitch in his whatever.
Well, I just, well, as Alistair says, like it might be a carryover from his old surveying days, but I don't know.
I mean, one of the things about azimuth that I read in the Jean Meus books is that that the marine people typically use azimuth 0 as south, as opposed to the astronomy people who use it north. So you do have to be careful when you're swapping from a nautical almanac to an astronomical almanac.
Okay.
Okay. And we'll clean up a couple of bits of that, edit the video, and then I guess over to you. Arnold has been very kind and produced a PowerPoint about Nova Herculis. Herculis.
And a
So-
few other novae, just to fill my time. So
And make co-host. There we go.
okay.
Okay, you should have control now and should be able to go to share screen.
Okay. Now, you see my screen yet?
Not
Or
yet.
no? Okay, I'm gonna try to find where the controls are on the meeting.
Mine are at the bottom, but sometimes they're up at the top and you just need to move the mouse over.
Yeah, well, I say share screen.
Mhm. And looks like it's working, and there it is.
Okay, so you see it now?
Yep.
Okay, so I'll play the, there you go. I played the screen. Okay, so Alistair asked me to put this presentation together on the novae. Well, because we've had a few of these recent ones, 2021, we've had 2 already, which are went into almost barely just above naked eye visibility. So I took on the task and started doing some research on it. And this cover screen is something that was from the NovaCast article from Sky and Tel. So I thought I'd give credit to Sky and Tel for this one. Anyway, so some short definitions just to, we have some, common starting point. So nova or novae in plural is basically thermonuclear explosion that happens in the shallow atmosphere of a star in a binary system. So a star stealing gas from its companion accumulates or accretes the gas onto its atmosphere and heats it up, compresses it, and then eventually creates a thermonuclear explosion or fusion. And this could happen only once, or it could happen on a repeating basis, depends on how much material is available from the companion star. And it could be anywhere from a regular sequence star to a red giant to, so typical regular sequence stars as companions. But because stars evolve at different rates, the other star might have evolved faster and become the white dwarfs, which means that it is now, still a massive star, but it now has gravity to attract the gas from the other companion. So, and then I put in the definitions where, since we're on the topic of nova, I'm not gonna spend too much time on supernova because these are galactic, typically way more bigger explosions than nova itself. So I thought, yeah, I'll take a look at some definitions, and it turns out that type 1a supernova is similar to a nova, except that the differences are when the explosion occurs in a supernova, it literally destroys the star and tears it apart, and therefore, not much is left other than maybe a nebula eventually. And then, of course, type 2 is a more cataclysmic event where a massive star, typically greater than 8 times the sun's mass, would eventually run out of its material, and therefore gravity takes over, and the sudden collapse of the star creates this massive explosion, and again destroys the star, and with a luminosity that's way brighter than any typical nova, and it would outshine its host galaxy, and therefore become visible, to the rest of the universe. Anyway, so having those definitions put in there, so at least we know what we're talking about. So yeah, by the way, if you have any questions, or just feel free to interject and ask your question away. Okay, back to the more timely topic of novae. So there's 3 types that I found out. So there's the classic nova, which I described as a system where a binary star steals hydrogen gas from its companion and eventually, causes a thermonuclear explosion, and the light from that explosion is what we see as the new star. And then if this happens on a recurring basis, then that's the second classification, where you have enough material where this event happens on a regular basis until the companion star runs out of material. And I didn't realize this third one that I just found out from my research was the dwarf novae, which is of this type, the Mu Geminorum type, which they have, well, quite recently, they have discovered it a long time ago, but just recently with better instrumentation, figured out the mechanism for it. And it's a novae which is not as bright as the typical classic one, but due to probably differences in the flow of material, or viscosity, or because binary systems are all different kinds. So under certain conditions, if the orbital days or the orbital period between the 2 stars would be in days, then there's enough conditions, right conditions for the novae to occur. But if the stars are much further apart, it may take a much longer time, or it may not even reach a critical point where you have an explosion, and therefore there might be just enough material to brighten the accretion disk and create an increase in magnitude, and therefore then the star becomes more luminous than it actually is. So yeah, so that's just the third type. So anyway, the ones that we're talking about are the classic type, or the recurrent types, which are classic as well, and they are more frequent. They're much fainter than supernovae, but they are more frequent in along the plane of the Milky Way, and according to this, it averages about 10 a year, and most are telescopic or photographic nova. But there are a few exceptions that go beyond the naked eye visibility, and that's what I'm going to talk about in the rest of my material. So anyway, the last portion of this paragraph, it mentions the last bright nova was V1369 Centauri, of course, in the southern hemisphere on December 2013, which reached a peak visual magnitude of 3.3, so which is relatively bright for and of course within naked eye visibility when it reached its peak brightness. Okay, so two things. Since this nova was never visible from our side of the world, I thought just for completeness, I'd say something about it. So this was discovered on December 2nd by Australian amateur astronomer, and as you can see from the finder chart, it's fairly close to Beta Centauri.
Nice.
So, which would have been really nice to see if we were in the southern hemisphere, because of comparison to compare it with the bright star Beta Centauri at its peak magnitude. So I didn't look up the magnitude of Beta Centauri, but this picture on the right with the La Silla Observatory in Chile, it shows the nova beside Alpha and Beta Centauri, and of course you can see the rest of the bright stars in Crux and the Closeup in that image. Okay, so just one more slide on this nova. You could see the peak outburst of the light curve for this nova. It was discovered shortly before its magnitude peaked in early December, and then it slowly dropped down. And then the chart, the inset chart on the chart on the left is blown up on the right side, and you can see how the visual, the nova reached visual magnitude of naked eye visibility from the time it was discovered in December until almost the end of January. So it was within naked eye visibility for a couple of months before it slowly receded.
Two questions, Arnold. One, were they able to find a progenitor star and know how bright it was before it erupted?
I didn't find any materials, but I'm sure that there's a lot of papers written about this nova. And I didn't go into the papers. I didn't have the credentials. Well, I didn't go further into the research, but I'm sure because they were really interested in what happened, this bright nova, what happens to the remnants of that nova, and after it faded away, because they wanted to separate the spectra from the spectra of stars that were more or less the progenitors of this nova. So I'm sure there's quite a few studies made. If you just look at research on V1369 Centaurus, you'll find some scientific papers written on it.
Okay, second question, is that a double peak that I see around the 5th and then 15th of December, or is that just muddled data?
Yeah, it's a double peak actually. There's actually a few peaks.
See 'em.
Yeah, but it stayed above naked eye visibility for a couple of months. Like it didn't fade away right away, so it stayed within visible visibility limits or whatever.
Thank you.
Okay, so that brings us to V1405 NovaCast 2021. This was discovered earlier this year by Japanese, I believe he's a professional astronomer, Yuji Nakamura, on March 18th, 2021. And at the time he discovered it, it was below naked eye visibility, magnitude 9.6. And then it brightened to about 7.5, which is still below naked eye visibility for 4 weeks. However, well, here's some pictures of it. These are from Sky and Tel article, by the way, which shows the location of the nova with respect to Cassiopeia, and a deeper sky image showing the nearby NGC 7635 and Messier 52. So yeah, and it was quite visible for us as well from our location. So this picture, this article was on May 9th, by the way. So quite a few months after. So these are my pre and post NOVA images, and Abdur kindly put an AVI together that blinked the two images together, so it's a little bit easier to see where it is. Anyway, so the surprise was, well, when we took those images and looked at it, it was probably in April time period, and then the light curve for this nova suddenly peaked into naked eye visibility around the 10th, the week of the 10th of May or 9th of May. So these are AAVSO charts or whatever. So you could see where around maybe the 5th of May or so, it started brightening up into naked eye visibility range. And that was a surprise. They thought it would just fade away. And this is a much longer time period of the AAVSO charts. And you can see that the light curves actually did peak around that time. So between the week of May 9th and May 16th. So it stayed above magnitude 6 for probably about a week that it was visible to the naked eye. Okay, and then I found this higher resolution imagery from this guy's John Chumak, Galactic Images. So I thought I'd post it as well because it had a much better higher resolution image of M52 NGC 7635. And I annotated it to put in the magnitudes for the different, the brighter stars in the surrounding area. So for example, this star here is magnitude 7.8, so approximately 8 magnitude. This blue one here is about 9th magnitude. This other blue one is about 6.6, and this blue one here is about 7. So this was at its peak, so around 13th of May. So typically around its peak brightness, which is about 5.5 or there, just within the naked eye visibility range. So yeah, so I added the annotation for these stars in this high resolution photo, and the magnitudes as well, just for comparison purposes, see how bright that nova was. Okay, that brings us to this current nova 6V1674 Herculis, which I haven't had a chance to look at. But anyway, so this was discovered just a few days ago on June 12th by another Japanese astronomer, Seiji Ueda. Photographically using a Canon 6D with a 200 millimeter lens. I believe he had it set at about 135 millimeters from his discovery photo, using 6-second exposure. So he found it shining at magnitude 8.4, so it's below naked eye visibility. But it briefly, some other observer managed to observe it at magnitude 6.4 a couple of hours later. And there's this other photo here. I think it's by Michael Jaeger, showing how red this star is, which is the hydrogen alpha light coming from that nova. So left side is the finder chart. It's fairly close to Epsilon Aquila, almost in the Aquila constellation. So it's on the edge or the border with Hercules. And yeah, this photograph was taken, I believe, fairly close to the time that it was discovered. Okay, so I included this another photo that I found on the net by Paul Sutherland. This was taken the 13th of June. And again, there's Eta, Aquila, Zeta, and a few other stars in the area with the magnitude, showing the nova compared to these other bright stars. So not as quite spectacular as the other image. But anyway, so here's the light curve so far. It hasn't been much generated for it, but it's just slightly below naked eye visibility as far as the recorded observations from the AAVSO. So it's only been a few days since its discovery. So yeah, so I think it might be on a decline as well. So by the time we get some clear skies around here. Okay, so that's all that I have to say. On the AAVSO website on this nova, it just says, please continue observing this nova as it continues to evolve. So, and that's it. That's my presentation.
Thank you very much, Arnold. Yeah,
Okay. So
looking forward to having a look just in binoculars, and should be able to pick that out from the backyard and give it a
yeah.
follow.
Well, I'm just wondering if anybody has gotten up at 3 o'clock in the morning to look at the, Aquila or Altair and see if they can scan for that star, beside Epsilon Aquila, and if they can pick it up in binoculars. So I haven't done it. So.
I have not done it.
It's it's reasonably high up. It'll be up above my trees after 1:30 or so. So
yeah.
But yeah, it shows it's worth, especially the weird behavior of the other one.
Yeah, well, yeah.
Following these things, pretty cool to see the sky changing.
Well, it's just quite unpredictable, especially for nova. I was intrigued by that Nova Centauri, because of course we didn't see it from here, but would be interesting to listen to amateurs down south who've seen it and report on its behavior, so, seeing it peaking like that. So yeah.
Okay. If there are no other questions, either about the topics here or any other general points, then this Astro Cafe will come to a conclusion. So thank you very much for watching. Thank you for preparing that. And we will get out there and observe this